Welcome, student. Today we are going to discuss a few more problems about optimization. So recall this was the guidelines from the last time. Uh, so we'll come back to it when we are doing a problem. So consider the following problem. So do dogs know calculus? So in 2003, Professor Tim performed an experiment with his dog Elvis. So what Tim did was he threw a ball into the river and he wanted to basically see what path will Elvis take or how will Elvis retrieve the ball. Okay. So now there are two paths Elvis could have taken. Elvis could have just jumped into the water and swam diagonally across to the ball. This would minimize the distance to the ball, right? The second path Elvis could have taken is Elvis could have ran until this point C, let's call this C, and then jumped into the water to get the ball. So now note that this is a perpendicular distance. So this is the shortest distance of ball and the shoreline. So he could have minimized the time in the water. Okay. So this is the actual picture. So Elvis with the ball taped and ready to be tested. Interesting. So now question is, what path did Elvis take? I mean, did it took either it jumped just into the water and ran to the swam to the ball, or did it ran to the nearest point to the ball on the shore and then swam across to get the ball? Surprisingly, Elvis took neither. Instead, Elvis ran partway here, and then from this point he jumped into the water to get the ball. Okay, diagonally. So then the question is, why did Elvis take this path? What does this path minimize or maximize? Right? So curiously, Elvis took the path that minimizes time it takes to reach the ball. Interesting. So by using calculus, Professor Pennings was able to show that Elvis almost took the path that is close to the optimal solution. Right? And this was published in the College Mathematical Journal. And here's a link for it. So let's try to see if Professor Penning's conclusion was correct, or let's try to see what is the optimal solution in terms of time. So let's see what is the smallest amount of time required to go to the ball. So we need some more details here. So let's look at the details. So Professor Penning threw a ball into the water as shown with the given distances. So this distance to the nearest shoreline is 5, and the distance of ball to the nearest point in the shoreline is 7 meters. Now, so to retrieve the ball, Elvis basically ran 4 and then jumped into the water to get to the ball, right? So he ran 4 instead of all the way 5, or instead of 0 and then jumping in. So Professor Penning measured that Elvis' running speed and swimming speed can with this, and found out that Elvis can run 7 times faster than he can swim. Using calculus used calculus to show that the path Elvis took minimizes time it takes to reach the ball. All right. So we'll try to optimize. Now we want to optimize what? We want to optimize the amount of time taken to reach to the ball. In particular, we want to minimize it. So let's see how we'll use optimization guidelines to set up this problem. So what are the optimization guidelines? Let's go through it again. Identify what has to be optimized and what the constraints are. 1. And draw a diagram if appropriate and label it. So we have found out what we want to optimize. So the amount of time taken to reach the ball has to be minimized. So it is the time to reach to the ball that has to be minimized. Now we'll draw a diagram. So let's assume that Alvis run along the shoreline at a point D, this point D, and then jumps into the water. Let X be the distance between C and D in meters. You'll say, why didn't you take this part as an X? You can do that as well. The thing will work the same way. Okay. So this is 7. So I'm taking this part and drawing it here. So it's literally a triangle, and this point D is measured here, written here. This point is C, drawn it here, and A is where Elvis is standing at the beginning at time t equals to 0. So now let's see. So what is the total running time? So he ran from A to D. So the running time is going to be AD. So note that velocity speed equals to distance upon time. So this would mean time equals to what? Time equals to distance upon speed, right? You bring this here, bring this down. However, we don't know exactly what the speed is, right? The only thing we know is that Elvis can run 7 times faster than he can swim. Okay, so in that case, let K be the swimming speed, then 7K is going to be what? Running speed, right? So in this case, it's going to be, he ran from A to D, which is 5 minus X, divided by speed, which is 7K. Similarly, Elvis, for swimming time, it is distance, which is BD upon K, because the swimming speed is K. So what is this distance? You can use Pythagoras theorem here. This is X, this is 7. So by Pythagoras theorem, the hypotenuse is going to be 7 square plus X square root, which is X square plus 49. So we get, so X square plus 49 square root divided by K. So this is the time taken to basically to go from where A to B using different paths, right? Now, what is the domain of this function? Note that this X could have been here. That means Alvis ran all the way and then jumped into the water to get the ball. Or X could be 0. That means what? Elvis basically jumped right into the water to swim to the ball B. So the domain of this function is 0 to 5. So here we have taken care of the following. We have taken care of the variables. We found out the formula. We also give it a name T of X. Now the next step is to find the critical points of this. So let's take derivative of this. T prime X. So this is your T of X. So T prime X is going to be, first part is 0, so minus 1 by 7K plus 1 by K times derivative of this has to be done using chain rule. So 1 by 2 square root of X square plus 9 times derivative of inside, which is going to be 2X. Okay. And then you cross multiply and simplify it. So this is going to be, multiply top and bottom by 7 here. So I have minus 1 by 7K plus 2. So 2 times X. 2 will cancel actually. So we'll get we'll get x upon k times x squared plus 9, but we want 7, we want to make denominator, so we want to cross multiply and simplify. So when you cross multiply and simplify, you'll get what? You will get, you'll get, so k is common, so we'll keep k common. So square root of x squared plus 9, right? The minus sign there, plus 7 times x, 7x divided by x squared plus 9. So now t prime x is 0. This implies the numerator is 0. That means 7x minus square root of x squared plus 9 equals to 0. This implies 7x equals to square root of x squared plus 9, 49, my bad. Square on both sides, so you get 49 x squared equals to x squared plus 49. This would imply 48 x squared equals to 49, and that would imply 49 by 48 equals to x squared. And then taking square root on both sides, you get x equals to plus or minus 7 by 4 square root of 3. Out of this, you will reject the minus 1, x equals to minus 7 by 4 square root of 3, since that doesn't belongs to 0 to 5. And since 7 by 4 square root of 3 belongs to 0 to 5, that is the only critical point we will consider. The second way to find critical point is t prime x does not exist, but note that denominator is always positive, right? And k is a positive quantity because after all, it's a speed. So in this case, there is no such x for which t prime x equals to, t prime x does not exist. So we have taken care of finding the critical point as well, according to the guidelines. Now we need to compare the values at the endpoints if they are given. In this case, we are given the endpoints as well, right? So first, let's find the value of t at the critical point and the endpoint. So t of 0 is putting 0 in this equation here. So if you put 0 in this equation, you'll get 5 by 7k plus square root of 49 by k. So 5 by 7k plus square root of 49, which is 7 by k, which is going to be 54 by 7k. Then you substitute 7 by 4 root of 3. You will get 5 plus square root of 5 plus 28 square root of 3 by 7k, and you approximate it to this. Then you have t of 5, the other endpoint, you get 7 times square root of 74 by 7k, and you get 60.2 divided by 7k. Now out of this, which one is the smallest value? Note that 7k, you're dividing by the same number, same constants, k, 7k, 7k. So now numerator will decide which one is the smallest, and you get that t obtains the minimum value at x equals to 7 by 4 root of 3, which is roughly what? 1. So therefore, the optimal path to minimize is to run for 5 minus x, right? Because running was 5 minus x. That is going to be 5 minus 1, which is 4 meters along the shoreline, and then the rest to swim, which is what Elvis did. Very surprising, right? So that's the idea, right? Now let's look at this next problem. So this is an example using trigs and limits. It will become clear what is this limit thing about. So a painting in the art gallery has a length of 3 meters and is hung so that the lower edge is about 1 meter above the eye of observer. How far from the wall should the observer stand to get the best view? Okay, so the idea is you have this painting here, and it has to be hung 1 meter above the ground. Yeah, that is what is given to you. An observer is standing, so observer will stand somewhere here, right? So here's the observer. Okay, so this distance is from the eye of the observer is 1 meter, right? Now, how far should he stand to get the best view? So generally, what does it mean by best view? Best view means you get a best view of something if this angle Suppose you're seeing an object. This is the object. The bigger this angle is, the better view you get, right? So think about it. If you have really small angle of view, then you can't really see the object, right? If the angle of view is 0, that means you are not even seeing, you're seeing object as a point. So of course you don't get the best view. So the bigger the view is, the bigger this angle theta is, the more details of the picture you will get, right? So we want to, what we want to do is we want to maximize the angle of the object which it subtends on the eye of the observer. Okay, so let's just draw this independently. Yeah, so here's the thing. So we have a picture which is 3 meters of height. There's an observer. This is the view of observer, and this distance is 1 meter. This is the angle theta, and we want to maximize this angle theta, which is on the eye of the observer. Okay, so how do we do that? Well, we'll extend this distance be x, how far the observer is standing from the picture. Let this angle be, so now what other tools we can use really? How can I relate theta with basically 3? Yeah, I mean, if I want to really use trigonometry, first of all, it's not a right angle triangle, so no usual trigonometric ratios will work right away. We'll have to do something else. Or notice the following: if we call this angle as beta, then what do we get? If you take tan of this total angle, if you choose to call it alpha, you can. So tan of theta plus beta is what? So now tan of this angle is opposite side, which is going to be 4 over adjacent side, which is x. So therefore, what do we get? Therefore, theta plus beta equals to tan inverse of 4 by x. Now, but we are looking for theta. Thankfully, beta can also be written as tan beta is opposite side upon adjacent side. This implies beta equals to tan inverse of what? Tan inverse of 1 by x. So theta is tan inverse of 4 by x minus beta, which is tan inverse of 4 by x minus tan inverse of beta, which is tan inverse of 1 by x. So this is the angle you want to maximize, right? And what is your domain? Your domain is 0 to infinity, because you can stand as far as you want and you can stand as close as you want, really. But at that tan is not tan of tan inverse of 0 is 0. So the domain has to be actually, you can also include 0 if you want, but tan 0 of 0 is going to give 0. So that's not going to give you anything interesting. So now we have drawn the picture, we have followed all the guidelines. So now let's continue with finding the critical points. So take derivative of this, so d theta by dx. So what is derivative of tan inverse of x? Derivative of tan inverse of x is 1 upon 1 plus x squared. So then the question is, what is derivative of tan inverse of 4 by x? That is going to be 1 upon 1 plus 4 by x the whole square multiplied by derivative of 4 by x, right? Chain rule. So this is going to be 1 upon 1 plus 4 by x the whole square times derivative of 4 by x is minus 4 by x. And you can simplify this further. You get 1 upon, so multiply this x square inside, multiply 4 on the top, you get 4 upon x square will cancel, you'll get x square plus 4 square. Yep. So this is your derivative of tan inverse of x. Similarly, you can check that derivative of tan inverse of 1 by x is going to be minus 1 upon x squared plus 1. Okay. So I go and we do the derivative here and simplify to make it look like this. Then you cross multiply. You cross multiply this and this and add them together. This is what you get. Right? So then theta prime equals to 0 gives me x squared minus 4 equals to 0. This implies x equals to plus or minus 2. But x equals to 2 is only in the domain because our domain is 0 to infinity. So in that case, what we have, x equals to what? X equals to 2 is the only critical point here. Now theta prime x does not exist will also give us some critical points if it satisfies, if any point satisfies that, but note that denominators are always positive, right? So therefore there's no such x. Now next thing we want to do is we want to draw the sign chart. So we take straight line, mark the critical point which is 2, and then check what is the value before 2. So take any value of your choice here. Let's take 1 and substitute it in the derivative. So if you substitute 1 in the derivative, what do you get? So let's see, let's substitute 1. So 1 square minus 4, negative, multiplied by minus. So negative times negative, positive. Bottom is always positive, so it's going to be positive here. Take a point here, say 4. So 4 square, which is 16 minus 4, positive, multiplied by negative is negative, and denominator is positive, right? Both of them. So negative on the top. So by first derivative test, you can see that 2 is what? Before 2, it was increasing. After 2, it's decreasing. So 2 is relative maximum. Okay. So what is 2 comma theta of 2? So when you put theta of 2 in this equation, you can use your calculator to check that you'll get 6.4 radians. Right? So theta of 2 is. Now we need to check at the endpoints. So the endpoints are not given to you. So we'll go limit as x goes to 0 plus of theta, and limit as, because we are on 0 to infinity, limit as x goes to infinity of theta. So limit as x goes to 0 plus of theta is going to be tan inverse of 4 by x minus tan inverse of 1 by x. Limit as theta goes to 0 plus. As it goes to 0 plus, 1 by x goes to infinity, and tan inverse of x, limit as x goes to infinity, is pi by 2. So this is going to be pi by 2 minus pi by 2 for both, and you get 0. Now let's check limit as theta goes to infinity. So this is going to be limit as x goes to infinity of tan inverse of 4 by x minus tan inverse of 1 by x. Now as x goes to infinity, 1 over x goes to 0, and tan inverse of 0 is 0. So tan inverse will go to 0. So this is going to be 0 minus 0 to 0. So thus the observer should stand 2 meters from the wall. X should be 2 meters to maximize. So that's it.